So, let's be part 4, lecture 4A, properties of the Poisson's bracket or curly bracket. Now, the first property I want to derive, to show, is any symmetric curly bracket AB is minus curly bracket of BA. So let's prove. We claim this. This here, we claim. See? Now, by definition, that's a curly bracket. You see, there's a gradient, pseudo-gradient transpose of A. This is the symplectic matrix, and this is a pseudo-gradient of B. Now, similarly, okay, by the definition, curly bracket of BA, you just swap B and A. Now, using transpose, attention now, this is a very important property to apply over here. So, XY transpose is Y transpose X transpose. This comes from the linear algebra. And I will apply this, you see, twice. I will apply this property twice over here. You see, the first application is X and Y red. So that's the definition of X and Y. You see, now this exactly like this. You see, so there's a transpose. Now this I expand X and Y here. Okay, this is Y and this is X. Y transpose, X transpose. You see, look at only the red. You see the red here. You see? Transpose. Now I'll apply again this property with the green one. Okay? Just on these two over here. Just look at here and apply this property over here. So I copy from to here, and then I'll apply this green one here. So this is just gradient AT minus G, you see, because the transpose of JT is minus J over here. You just go to the definition of the matrix, your symplectic matrix, and you see there, it's easy to show that these are symmetric, okay? So this case, the transpose of the matrix, the symplectic matrix is minus J. So this is from here. This is only the green one. You see, I'm applying the green one right over here. So let's put the same color over here. Okay, I'll put the green one here. The green one, there's a green one. You see, just look at there. You see? So the transpose of J is minus J over here. So that's straightforward. Then this minus comes over here. This is exactly the curly bracket of A and B. So this BA is minus AB, which is proved. Okay, let's move to bilinearity that we claim, the bilinearity. You see, this is bilinearity, A, B plus C. That's a claim. I want to show this curly bracket AB plus AC, curly bracket. That's proved. Because, attention, because differential operator is linear, I can expand the gradient B plus C is equal gradient B plus C. Because this here is just derivative. So the derivative, the first derivative is linear operator, is linear. So this I can write over here. You see? This one and this one. You see? Now, gradient of A plus B is equal gradient of A plus gradient of B. Since the operator is linear operator. Now let's apply this over here. So this is A, this is B plus C. So you're using parts. So there's a gradient of AT, gradient of B plus C. You see this over here, I will expand this, okay? Using this differential operator, the linearity of this differential operator. It's quite easy, it's easy. So expand this B and C. You see these two terms over here. I can expand using the property of differential operator is linear, okay? Just applied here. Then I can see clearly that this one here is the curly bracket of AB plus the curly bracket of AC. Similarly, we can prove A plus B and C. So the curly bracket of A plus B and C. You just develop this easy. So this, in this case, you see, you have a transpose. Attention now. You see, always I'll get the transpose of the first one, which is here, okay? I repeat J, and this is gradient of C. That's from definition. You see, if you see confused here, you just call A plus B as D, okay? So this, the gradient of D transpose plus times J gradient of C. You see, you just call A plus B as D, okay? And substitute over there. Then you expand this, okay? This is just analogous what I did over there. You just look at here and copy and see if it's correct for you. You see, that's the second proof, okay? Now, the third one, Leibniz rule. You see, in general, in calculus, you have the derivative of a product, okay? Then that is called, in general literature, you call Leibniz rule or product rule, okay? We claim, attention now, A, comma, BC, the curly bracket is B, A, comma, C, and C, A, comma, B. That's proof. Now, start computing, attention now, this, the application that applied. You see the pseudo gradient on this product over here. You see? So you can expand here using the product rule. Okay? Now it's B gradient C plus C gradient of B. Product rule or Leibniz rule over here. Thus you can substitute clearly. So again, that's a definition. Okay, again, if you have problem with this BC over here, you call this as D, okay? So this will be D, okay? You see the curly bracket AD is gradient of A transpose J, and this case pseudo gradient applied to D, the red one. Then you substitute D by BC. Then here you can just substitute the gradient here by the sum over here. You see, you just take this one, you see, this one here, and you just substitute, okay, on here, okay. So substitute D on here. It's quite easy. Now expand, distribute. You have distributive. So there's a property, okay? If you distribute, okay, this is, then you substitute over here. That's expand, that's quite easy, you see? Now, you see, you have this, the add over here, okay? You just transform this into two terms, okay? Add in two terms, just over there. Then you see the definition of the curly AC, C times the curly AB. Thus, you see, the in this case, okay, we see clearly that the curve vector A, BC is BAC plus CBA. It's proved. Now, the fourth, okay, property is a little bit long, okay, that then I'll show clearly this, okay, in the next lecture. Okay, this is lecture for A. Next lecture for B, I will show the Jacobi identity, which we already derived when the derivation of the Lie bracket, see, one of the properties of the Lie bracket is the Jacobi identity. This identical, okay, identical way to prove, see, but I will do this in the next lecture for B, okay, it's still in part 4, okay.